Semaphore is a process synchronization tool using which we can able to avoid data inconsistency that occurs due to race condition. Semaphore is an integer variable where it can have both positive and negative values. We can apply two types of operations on semaphore. One is wait and another one is signal. Wait is indicated using the symbol P and signal is indicated using the symbol V. Whenever the wait operation is invoked, the semaphore variable gets decremented, and whenever the signal operation is invoked, the semaphore variable gets incremented, which means we can able to identify how many processes are waiting in the queue to access the critical section on seeing the negative value of the semaphore. And similarly, we can identify how many processes have completed executing this critical section on seeing the positive value of the semaphore. There are two types of semaphores. One is counting semaphore, another one is binary semaphore. The counting semaphore can have both positive and negative values, whereas the binary semaphore can have only two values, 0 or 1. 1 means the mutual exclusion is enabled, and 0 means the mutual exclusion is disabled by a process. Let us consider an example. There are two processes, P1 and P2, in which the statement S1 from P1 has to be executed first, and then S2 from P2 has to be executed. Hence, when the statement S1 from P1 is executing, P2 is in the waiting state. After S1 statement was executed by P1, it invokes the signal so that P2 can start executing S2. There are three classical problems of synchronization. Let us see one by one. First one is bounded buffer problem. In bounded buffer problem, there are n number of buffers which uses three semaphore variable, mutex for mutual exclusion and full to ensure whether all the buffers are full for the consumer process to consume the data, and another semaphore variable empty to ensure whether all n buffers are empty for the producer process to load the data. Let us see the code for the producer process first. The producer process produces some data and it waits till all the n locations in the buffer are empty. Hence, it invokes the wait on the semaphore variable empty. Once when all n locations are empty, then it invokes the wait on mutex. Means it applies mutual exclusion so that the critical section is accessed only by the producer process. Here the critical section is nothing but loading the data item produced by the producer into the buffers. Now it adds the n data items in the n buffers. After the loading operation, the signal is invoked on mutual exclusion such that it disables the mutual exclusion, and then it gives a signal that all n locations in the buffer are filled, so that now the producer process can the consumer process can consume the data. Similarly, see the code on consumer process. The consumer process waits until all n locations in the buffer are filled by the producer process. Once all n locations are filled, then it invokes the mutual exclusion using wait of mutex. Then it starts removing the items from n buffers. After all n items are removed, then it gives a signal on mutex, means the mutual exclusion is disabled. Then it gives a signal that I have removed all the items in the buffer so that the producer can able to start producing the data and load the items into the buffers. So it invokes signal of empty. Now it consumes the data whichever it has removed from the buffer for their operation, and now the producer process can start loading the data into the buffer. The second classical synchronization problem is reader-writer's problem. Readers are those processes which have the rights to read the data, but any number of processes can read the data at a time. The writer process can both read and write or modify the data, whereas only one writer is allowed to modify the data at a time. There are two semaphore variables and one integer variable used for the implementation of reader-writer problem. The first semaphore variable, read-write mutex, is used by the writer process. Whenever the writing operation is carried out by the writer process, it enables a mutual exclusion using read-write mutex, and after the completion of writing operation, it gives the signal on the semaphore so that the next writer can able to modify the data. The second semaphore, mutex, is used by the reader process whenever the read count variables is going to be updated by the reader process. The code for reader-writer process is shown here. Let us see the writer process first. The code at the left is the writer process. First, the writer process invokes. This code shows the implementation of reader-writer's problem using semaphores. The writer process enables the mutual exclusion before the writing operation is performed. All other writing process will be in the waiting state. After the writing operation was done, it gives the signal that the writing operation has been completed so that the waiting process can able to next modify the data. In case of reader process, two important points has to be noted. Whenever a reader process is updating the read count value, it has to enable the mutual exclusion. Similarly, the first reader process has to ensure that the writer process has modified the data and the latest modified data was accessed by the reader process. Similarly, the last reader process has to ensure that the data is modified after the reading operation is done. Let us consider the first reader process is reading the data. Hence, it enables the mutual exclusion. Then it increments the read count value. If this is the first reader process, then the read count value is incremented to 1. And now we check whether this is the first reader process. If read count is equal to 1, then this is the first reader process. So, it has to ensure whether the writing operation has been already over. If not, it has to wait till the signal is received from the writer process. In case if the if condition fails, that is, this is not the first reader, then it can able to disable the mutex by giving signal, and then it can start reading the reading operation. The same operation is done by the second process, whereas all the other process except the first process, the if condition will not be satisfied. Similarly, whenever a reader process completes its reading operation, it has to decrement the read count in order to keep track of whether all the reader process have completed its reading operation. Hence, after the reading was over, the mutex is enabled by the reader process, then the read count value is decremented. To ensure the last reading process, an if condition is given. If the read count value becomes 0 again as initialized before, then this is the last reading process, and this process gives a signal to the writing process that the reading operation was completed so that it can perform the next write operation. Now it also disables the mutex, and finally the process ends. The third classical synchronization problem is dining philosopher's problem. There are 5 philosophers sitting in a circular dining table. where each philosopher is considered as a process. There is a commonly shared resource at the center of the table, which is nothing but a bowl of rice. Each philosopher, in case if they takes one chopstick in their hand, then the system will enter into the deadlock state, because every philosopher needs both the chopsticks to eat the rice, which means they need both the chopsticks in order to access the commonly shared resource. The philosopher may be in any one of the states, such as he might be in eating state or he may be in thinking state. So in order to handle such deadlock situations, allow only 4 philosophers to sit on the table, or restrict the philosophers to access the resource only if both the chopsticks are available. Similarly, every odd numbered philosopher is allowed to take the chopstick at its left hand side and then the chopstick at the right hand side. If only both the chopsticks at the left and the right are available, he is allowed to access the resource. So according to the algorithm, a philosopher will enter into the eating state only if he gains both his left and right chopstick. This is what shown in the code. Both chopstick I and I plus 1 is taken by the philosopher to enter into eating state, whereas the neighboring philosophers has to wait to acquire the another chopstick. Once when the current philosopher who is in the eating state completed its work, then he will give signal for the ith chopstick and I plus 1 chopstick. And those process who are waiting for those chopstick, now they can get the chopstick and continue their process.